Our second session deals with the topic Sustainable UAV Technologies, Hybrid Powered Drone Solutions, Powering Eco-Friendly Transportation. The session will be handled by Mr. Murali Krishna Boddu, sir. Thank you everyone for your active participation in the first session. Now, moving forward to our second session, we step into one of the most exciting and fast advancing areas of modern technology, the world of UAVs and sustainable aerial mobility. Our second session deals with the topic Sustainable UAV Technologies, Hybrid Powered Drone Solutions Powering Eco Friendly Transportation. To guide us through this significant topic, we are privileged to have with us an international expert, Mr. Murali Krishna Boddu, sir, who is a distinguished academic and researcher with over 22 years of teaching and professional experience in electrical and electronics engineering. He holds a bachelor's degree in electrical and electronics engineering and a master's degree in power electronics, providing him with a robust foundation in both theoretical and applied engineering domains. His research expertise encompasses hybrid energy storage systems, power electronics, and artificial intelligence applications in engineering. Over the course of his career, he has contributed significantly to the advancement of the field with 12 papers published in reputed international journals and 16 research presentations at international conferences. Currently, he serves as a faculty member at the College of Engineering and Technology, University of Technology and Applied Sciences, Shinas, where he is actively engaged in teaching, research, and mentoring students in advanced engineering subjects. His extensive experience, research contributions, and enthusiasm for academic excellence make him an inspiring and insightful speaker for this webinar. Sir, we are delighted to have you with us. I now warmly invite Mr. Murali Krishna, sir, to deliver this session. Sir, the stage is yours.
Okay, ma'am. Thank you for your kind words. Can you hear me? Hello?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Thank you, ma'am. Thank you very much for your kind words. And thank you to the MBC College for giving the opportunity to interact with the young budding engineers and the fellow researchers. Welcome to for the day 3, session 6 of Atal Online program, Smart Cities and Future Mobility, Technologies, Policies and Practices. So before going to the presentation, this is a disclaimer. Whatever my presentation, almost 80% I have taken from the literature. This is the work done by various researchers and scholars. And only 20% of my work I am presenting in the last part. So this material, you can use it for solely for academic and educational purposes. Coming to my presentation, mainly I will focus in 4 areas, especially growing countries like India. There are enormous amount of funding is releasing for the building of technologies, especially smart cities, where main aim is to reduce the emissions. So conventional transportation with the oil, which causes more of emissions, so that we need to go for reaching for net zero conditions as early as possible. So the main approach to this one is the future mobility. The future mobility is driving eco-friendly transportation. So in this regard, I'll go for the uh, one of the key and modern technologies called unmanned aerial vehicle. First, we will see the unmanned aerial vehicle applications in the smart cities. And next, we will go for the power system for UAV propulsion systems. Then we move on to the hybrid power system with the UAV operation, and mainly concentrate on intelligent energy management. So my most topic is with respect to applying artificial intelligence to the electrical engineering systems. I will demonstrate a energy management strategy, how a hybrid powered UAV can achieve the targets required for that. So first we'll go the what are the applications of UAV in smart cities. There are various applications, especially eco-friendly roles of hybrid powered drones in the urban and infrastructure management, urban air mobility, and passenger and air taxi services. Nowadays, you can see in some countries like Dubai, they have started already air taxis. So that is the technology. Then emergency services and medical supply delivery. During the flood conditions or bad weather conditions or emergency conditions, drones are supporting like a human. And mainly logistic delivery, especially Amazon, they have already started with the logistic delivery for efficient cargo transportation. And nowadays, most of the environmental authorities and flood relief NDRF types systems, they are already utilizing the drones for tracking air quality, emissions, and environmental monitoring. Along with this one, we have many other applications where a commercial drone can serve for different applications, especially electrical engineering, all renewable energies, they are condition monitoring they are doing with respect to drones, especially solar in the area of even they are detecting the drones, detecting the defects in the solar module or solar cell. So that is the technology. A drone connected with a thermal imaging camera can scan a defect in the solar module. So that technology, monitoring and data collection, delivery, aerial mapping, surveillance, especially traffic surveillance, and agriculture, especially in India, like country where paddy or the agriculture is the main source of income for many of the states. Nowadays, if you go and see the villages, they are using the drone for many applications, and flying photography and sample collections for. So there are various numerical applications you are nowadays seeing with respect to the drones. Now you can see the classification of UAVs, different applications. Suppose if you consider with respect to weight, they have micro UAVs, miniature UAVs, heavier UAVs. Suppose depending upon your flying height, low altitude, high altitude, medium altitude. Suppose if you have a social applications, special applications like submarine launched UAV, seaplane launched UAV, submersible UAV. Suppose if you have endurance range, you have a short endurance, long endurance, and medium endurance. Suppose number of wing types. So fixed wing type, rotary wing type, and flapping wing type. These are the various classifications of the UAVs that are available in the market. So as I mentioned, there is a wing type. Here you can see a tricopter means there are 3 wings. Hexa means there are 6. Quadra means there are 4. A fixed wing hybrid vertical takeoff and landing, and single rotor also there. And so these are the various types of UAVs nowadays available in the market depending upon their special need and application. So you can see different configurations. It is called Y6 configuration. So where there are three wings, they can move either in the clockwise and anti-clockwise directions. And quadra configuration, quadra plus configuration also. Quadra X configuration means the wings are arranged in the X form. Quadra plus configuration means the wings are can be steadily stay at the plus condition. Then if you are go for the multi-copter models, hexa X means there are 6 wings. Hexa plus means you can have a straighter. Then octa 8. Then octa plus means in the, so there are variety of wings and there are used for the special purposes. Then what are the various components? Now we see the what are the classification. If we go inside to this one, what are the various components? So the main components here, it is antenna. A antenna consisting of a transmitter and a receiver, control transmitter and receiver. Then a power distribution panel inside and the flight controller. And there are 4 wings attached with the 4 propeller motors, especially called BLDC motors. And there is an electronic speed controller. And nowadays we are using the camera. So camera is a part of the drone. So these are the various components of the drone we are using for different purposes. So if you see the orthogonal view of this one, the core components is frame and chassis. So you can see this is a quadra 4 wing rotor, the frame and chassis, propulsion system, and flight controller, power system, and electronic speed controller. And there are many sensors connected to this one because we need to gather more information and data. So for the purpose, sensors are there. There is a GPS for navigation and position tracking, gyroscope and accelerometers for stability and orientation, radio transmitter and receiver, and camera, what we seen. So these are the various components operating on a single power system, the source of power. Remember this one, these are all operating on a power system. So our aim is to discuss more on the power system on this one. So many components, they need power supply to operate that one. So whenever you are seeing a drone, it will fly, right? So a multi-rotor or a multi-captor has 3 directions. There is a movement. There is a movement, up-down movement, rotating around its own axis, sideways, forward, and backward directions. It can move in different directions. So it will move in the direction, upward direction, vertical direction. It can rotate its own axis, and it can go in the forward and backward directions. Then there are certain amount of forces we need to develop inside that one. It is called thrust. Suppose if you want to lift the drone, in order to descend or lift the drone, the lift is generated by propellers must be slightly less than the gravitational pull. Suppose if you are bringing the drone to down, descend. Suppose if you are ascend, we have to produce a force much higher than gravity. Suppose if you want to turn around the axis, the total force, one pair of opposite. You see here, there are 2 dark colors, 1 and 3 are in the same. So it is one to turn around its axis, the total force on one pair of opposing propellers must be greater than that of the other pair. So that then only it will turn around the other axis. You can see in these 2 pictures. So these also required the power. So now you know about how we can move in the upward direction and downward direction. Then how we can know the typical flight profiles. Flight profiles may be, you can see here is a typical flight profile. How we can represent in a 2-dimensional axis. X-axis we can take the time. Y-axis we can take it at the altitude. Altitude means how much height it can go. So the typical paths are planes, we can call it as, first one is called takeoff. because these are all very important while you are designing the power system for this. First one is called takeoff. Once you take off, it will go to the limited amount of height. Then again we apply more thrust. It will go to the climb. The second level is called the climb. Then cruise. Cruise means it will stays there and constant. It will go constant displacement or constant altitude. Then descent. Descent means it reduces the speed. Then again endurance. Endurance means it will remains in the cruise mode. Then landing. Landing will be in the different altitudes. So this is the total typical flight profile. So we can go with the geometrical analysis. This analysis we are doing with a VTOL method. It is called vertical takeoff and vertical landing. Vertical takeoff and vertical landing. So in this, how we can produce the force? The thrust is higher than the sum of gravity and drag functions, the lifting force for the vertical takeoff. Whenever there is a thrust which is more than gravity and drag forces, it can go for the takeoff. It moves along the flight path in the direction of the resultant four forces. Suppose we have four quadrupole wing, it is there. If four forces are resultant, when it will, you can see here Fs direction, Fw direction, the resultant it will go in the moving in the one direction. For the vertical landing, sum of the lifting force and drag becomes the lower than the gravity. So these are the principles of operation for lifting up, moving into the cruise mode, as well as the dragging down or descent into the. So these are all required power to operate. Remember this, these are all operate with a force. So as a typical, as I mentioned previously, how it will take off, how it will run in the cruise mode, how it will land. So there is a resultant force. If the resultant force acting in the upward direction, the lift will be taking off. Then if there is a thrust acting on the resultant axis, it will move in the red color. You can see here it is a red color. It will shows the direction of force. Same direction it will go. And here it is a landing. Landing is descending. The resultant force is less than the gravitational force. So based on this, the flight mode will be activated or flight profile will be operated. So these are all required, the power system inside that one to operate all the components. So this is the typical flight profile. You can see, as I mentioned previously, takeoff, climb, flight or task, or we can call it as descent and landing. So you can see the yellow color one is the flight path. You can see the red color is the drive power, how much power you require, in each position or each flight time. So we required different amounts of power during the different flight paths. So for that, we need to design a typical power system to achieve these tasks. This is the typical power. I will show you another one. So here there is a hybrid power. You can see. So hybrid power means you can see the P load. Load is the how much amount of power required for this one. So which is supporting. Here you have a battery and fuel cell, which is supplying the during this flight path. So taking off, climbing, cruising, descending, and landing. So these are the different values of magnitudes of the power required to operate the drone. So this is about the power profile of an UAV. So now to operate the drone in different flight paths, we require different power profile. So now we will see what are the technological breakthrough through this one, how power system is designed for hybrid propulsion system. So first of all, we will see what is there inside the UAV system. Now we see the various components. Now we will see as a system. So UAV consisting of an energy supply system consisting of an energy storage system, energy management system, and energy converter. Remember, There is a storage device, there is energy management system and energy converter. So these, they supply power to the flight control system, which consisting of, as I mentioned, each component will require the power, right? So these power can utilized by sensors, controllers and actuators. And avionics also mission equipments and data storage and transmission. And there is a ground control tower is there, are we can call it as a controller, so where it will also operate with a different supply, but we are more interested in the energy supply system of UAV, energy storage device, energy management device and converter. This is in the ground control. So we are mostly interested in the energy supply system, which can serve for the all other components. Okay. So now a typical block diagram representation of a UAV propulsion system. As I mentioned previously, there is a energy storage system or a energy storage device like battery, supercapacitor, fuel cell. Then from that there is a converter, DC to DC converter, bidirectional especially, and there is a common bus. Why we require a common bus? Because you need to run the all the remaining components of US. So we have a common DC bus, then DC to AC. Suppose sometime they will use PM DC motor, PM AC motor, or permanent synchronous motor. So sometime they will use. So there is a brushless motor, PMDC or PMAC motor. From that we have an electronic speed controller, which will generate the PWM signals. So this is a simple block diagram. So where we have the power consuming elements and power generating and power conversion devices also there. So there is a power flow in the some devices bidirectional. The control signal will go from in the energy management system to the converter, electronic controller to the system. And data acquisition, they can take the data to the energy management system as well as controller system. So here the dotted pink color, you can see the data acquisition system. So now we require a different type of energy sources. So specific energy power comparison for different energy storage devices. So this is a general specific power versus specific energy. You can see the electrolytic capacitors, ultra capacitors, double layer capacitors, then batteries, then fuel cell. You can see there are the flying profiles also you can see. So with the advancement of fuel cells, you can go up to 10 hours endurance or the battery time you can get. So we will achieve with respect to the combination of all the, we will use the control different properties of different energy storage devices to benefit our flight profile. So you can see that the electrolytic capacitors will have more specific power, and the fuel cells will have more specific energy density or power density, they can call it. So now we have various types of energy sources. So this is the history of timeline of common PMFC fuel cells. So they started using from 2003 to recent 2025. So the endurance of flight time varies from 0.2 hours or flight time from 15 minutes to now they are reaching 3 hours to more than 3 hours. So with respect to the fuel cells. Nowadays, now with respect to the batteries also they are using in the different technologies with a lots of improvements in the battery energy sources, as well as from the solar powered UAVs also. This is the timeline representing, so where they utilized and used for different types of UAV devices for the, so there is a chance for using fuel cells, batteries, supercapacitors and the solar cells. So these are the different types of power sources that can serve as the power system for the UAV. So after seeing all these, so summary of the power sources, there are some shortfalls. One is called the specific energy. some devices having low specific energy, high density, then high power density, some sources having. Then if you combine all the components, if you have taken a battery, weight become a constraint. If weight is constrained, if you want to carry, because we mentioned in the smart city applications, we used this for the delivery applications. So payload capacity, you need to have more payload capacity, and flight time, then recharging and discharging of the power device. So now these are the shortfalls. Now we need to overcome these fault with our technology. So what is the possible solution for improving the shortfalls, what we discussed earlier? So there are 4 technologies now the researchers are proposing. One is wireless charging techniques. Suppose one battery is discharging wirelessly, because wirelessly they're going the wireless charging techniques. Then electromagnetic field generation, then battery swapping, then now the peak system is hybridization. Hybridization means combining 2 or more sources. So now we are more interested in hybridization. This is the one of the possible solution. These are also supplying in the different applications. My part of interest is on the hybridization. So hybridization means how we can go. So here I will show some researcher called proposed 3 different architectures: a battery source, DC to DC converter, and a fixed DC bus given to permanent magnet synchronous motor, a number of motors, because we are using a quadrupole, octapole, heptapole. Then second architecture, because the first technology is how they mentioned. The second architecture, in spite of DC fixed bus, they are going for a swinging bus. Swinging bus means voltage fluctuations will be there. So then DC to DC converter, and so these are the architecture 1 and architecture 2, supplying DC a DC to this one with a one source. Second architecture, they go for an hybridization. Hybridization means 2 cells, the fuel cell versus battery, coming to a DC bus, then feeding to the permanent magnet. So what their results shows is, so as per our flight paths, takeoff, ascent, descent, and landing, and there is a cruise. So we have a takeoff and a cruise, ascending and a descending, then cruise. So this is the normalized thrust required over a part of time. So this architecture 1 and architecture 3, so they have some losses in the system. They have more losses in the system because they consumed more power because of this combination. So then they will go for the, again we can see the required power output versus time. This is the, as mentioned, output power. This is the power loss. You can see the more power losses you can observe with respect to this system. And system efficiency, even though they achieved the architecture 1 only battery, they achieved 80, and hybrid fuel cell they achieved very less, because most of that one because of improper hybridization. Improper hybridization, they will go for the many of the power into a losses. So then they approached for the new approach. So this is with the fuel cell, alone fuel cell, and alone with the battery powertrain, fuel cell based powertrain. So they also see some amount of losses during the takeoff, and they applied with the different types of batteries. The lithium ion battery, lithium polymer batteries. So they observed there is will amount of loss they can see. The efficiency you can see around 40% only. With the you can see in the cruise mode also we can see only 60% of this one. So then they can go for the, you can see there are numerical losses they mentioned by the scientists, researchers. They gave in detail in this paper. Now there are some losses if you are not properly hybridized. So that's why we need to go for hybrid powered UAV operation. How we can do the hybridization? Hybridization they can do in two modes. One is called passive hybrid power system. So fuel cell and lithium ion battery with the unidirectional power to the load. So I'm simply representing load as propeller motor. So fuel cell lithium ion battery, and there is a battery charger, and you can send it to the motor. So this is the passive hybrid power system. And there is an active hybrid power system also. They mentioned the four type of architectures: structure A, structure B. You can see the parallel combinations and different fuel cell powering the battery. There is a bidirectional structure and structure D, structure C. So this is the where they claim that there is a less number of losses if you structured the hybridization. So now if you see the structures, so fuel cell, battery and supercapacitor connected to a BLDC motor, fuel cell, battery and connected with a BLDC motor. Because you have multiple number of sources, you need to go for energy management system. We have energy management. So if you go for multi number of sources, we need to access their complementary benefits. We need to go for the energy management. So now we required, if you go for the proper hybridization, we required another amount of the energy management, that too intelligent energy management system for enhanced performance in the hybrid powered UAVs. So this is the simple block diagram representing a hybrid power system. It may be any combination of battery, supercapacitor, of any architectures connected to a DC to DC converters and to a common DC bus and DC to DC converter. This is same block diagram. This is the hybrid system. So first we will see some energy management system with a battery and fuel cell. They used a buck boost converter for battery and interleaved converter, DC to DC converter for a fuel cell. And they used a quadra wing UAV connected to a DC bus. So from this, they used two different flight paths. As I mentioned previously, takeoff, climb, cruise, descent, endurance, and landing. So the required UAV speeds, because we have a speed measurement device also there in the onboard. So we have different flying modes and required power. This they calculated while designing the UAV also. So these are the different powers. So we required different speeds, required different nominal power as the DC bus input. How much amount of DC power input to this one? So we need to monitor all these parameters for the efficient operation. So design requirements for energy management system. You see the different flying mode requires different speeds. Different speeds require different nominal power. Different nominal power requires and supports the different bus input power, as well as the, now we need to give that power to the propellers, because this will only operates. So for proper design, the design requirements for energy management system: for a fuel cell converter output power; for battery SOC; for supercapacitor voltage; and DC bus, at the DC bus you require a DC bus voltage. So these are the four parameters we require while you are going for the proper energy management system, because we need to have maintained these parameters within the tolerance, so that your UAV cannot be drained as fast as low as possible. Means they will properly manage. So now you are designed the UAV system, you need the performance criteria, means on which parameter you are telling it is efficiently operating. You are operating with multiple devices. So the performance criteria for energy management strategies is effectively distribute the power during dynamic mission phases and minimize because we are using a hydrogen fuel cell, minimize the hydrogen and battery stress, thereby enhancing the overall system endurance and reliability. The main aim of our is we have to get the overall enhancing, means we have long endurance and more reliable. So what are the parameters? Hydrogen utilization. So what we have, minimize the hydrogen and battery stress. So hydrogen utilization will be less, hydrogen mass consumption will be less, battery SOC will be less, and battery energy utilization will be. So these are the four parameters will define the efficient operation of the energy. So for that one, they used one research paper recently they published with the fuzzy logic and ANSI. So they used this control strategy, fuel cell converter control scheme as well as battery control scheme. Then they achieved the performance criteria with the two type of management strategies, fuzzy logic and ANFIS. So hydrogen utilization is 74.9%, and with the ANSI 82.86%. Hydrogen mass consumption, very less amount of hydrogen they utilize, and battery SOC, they have seen enormous battery SOC. So 75 to 69 range and 75 to 70 range. So this is the battery energy utilization, only 6% utilized during this one, remaining part it will utilize. So here the ANFI artificial and fuzzy interface here they are using. So this energy management strategy, they got very good performance. With this as the basic idea, we implemented using the next part, machine learning as well as the deep learning topologies. During this, they achieved the fuel cell power versus load. You can see the fuel cell load as well as the battery powers. So the fuel cell power remains almost constant, and the load and battery, so they are following the same profiles. Then you can see the DC bus voltage. They mentioned that DC bus voltage they require 24 volts, and the current that is supplied to the motor of same as the energy profile. So now we'll go for the big architecture. We move from fuel cell battery to, we'll go with the four energy sources: fuel cell, battery, supercapacitor, and a solar cell. We have different converters for different strategies and a DC bus. Coming to the propeller, so this is the maybe future design. This is maybe the design. So for this, how energy management strategy we performed is, we have the four sources and four converters. In that we have an intelligent controller. We go for the optimization algorithms, rule-based control, machine learning modules, or you can give it to the constant bus. Then we have a UAV propulsion system and flight and environmental data. So the power is received to the this one. This is the architectural diagram for energy management. So as per this, first we implemented with a rule-based system. Energy management is a rule-based system. So the same profile what they used is, we used also the same amount of data we utilize. So same rule-based system only we implemented. For the rule-based system, so the weight, as I mentioned previously, we are using more components. Weight is another constraint, right? So as we go for the multiple number of components, these are the weights, that is almost it is reaching to the more than 20 kg of weight of UAV, so that we need to go with the more power. So this is the UAV power over time. So we simulated using MATLAB as well as we simulated using the Python coding. So this is the UAV load profile we achieved for that one, because this is the amount of power supplied. We can see here, there you have more power utilization there. Now we have designed with the less amount of power over a duration. Then fuel cell is supplying. You can think that the profile is same. You can see here, you can keep in mind the profile is this one only. First takeoff, then climb, cruise mode, descent, endurance, and landing. During the different profiles, you can see the UAV loads. And there is some two different effects which will act on this one, because if you are considering the wind speed as well as temperature taken into consideration, so sometimes the batteries will drain very fast, sometimes, so the complementary actions they utilize. So this is the power contribution by battery. So initial stage, then battery will be off, then during this is the landing as well as descending the Helios. Then supercapacitor power contribution over the time. Then battery state of charge. Battery state of charge from 80% to around 69% during the flight time. Then supercapacitor voltage. They need to maintain supercapacitor voltage also. There is not much difference, because it is almost 4 to 5 volts drop. Then hydrogen consumption, so very less, you can see 0.010. I will show you in the results, you can easily understand. So this shows that one we implemented with the rule base. I will show you all the results in the comparison. Then we will go with the machine learning based for this same profile. You can see the duration of the minutes versus the flight phase, because now we implemented with the same flight with a different approach. Pre-flighting checkup, then taxi takeoff, climb to altitude, cruise mode, operation, then different flight modes. So this is the deep learning approach or machine learning approach, what conditioning electronics. Then we have implemented with the different deep learning layers. So the results you can obtain is fuel cell power. You can see there is a drastic change in the power management. Previously fuel cell we have different, and battery profile also changed. Then supercapacitor is now, previously battery is supporting, now supercapacitor is going for the high thrust when it is taking off and when it is landing. Then the battery SOC remains almost the same, because 82 or 59%. Then supercapacitor voltage over time, so then 25 volts, and there is a drastic down of voltage because of the machine learning approaches. Then cumulative hydrogen consumption increased a little higher, because fuel cell is so this is the total comparison, the total load energy comparison over a flight mode, rule based versus the AI/ML placeholder approaches. This is for fuel cell energy contribution, battery energy contribution, and supercapacitor contribution. So this is how the four sources are supplying their contributions during the different flight modes. Then with a deep learning approach, now the same profile we are applied to the deep learning base. So you can see the load power versus motor power drawn. Load power and motor power drawn. Load power means total amount of power utilized for all the components. Motor power means only propeller motors. So there is higher amount of power than compared to the. Then motor efficiency, we achieved almost 85% of motor efficiency over time because of this deep learning approach. Then power consumption, you can see the different profiles over the various ranges. This is the power fuel cell power contribution over this one. Then power super capacitor. Now you see the super capacitor, a different topology you observed here. Then motor drawn compare over time. So this is the rule based versus the power, how we achieved this one. So this is the approach we used for the reinforced learning, we used the different agents, state vector, RL algorithms we implemented with the DQ and DDPZ. Even we given with the actor critic algorithm, there are the reward functions, minimize the H2 consumption. We need to take out the degradation of the battery, degradation of the supercapacitor, maximize the motor efficiency, maximize the SOC limits, then SOC of the supercapacitor and power requirement met also. So these are the reward functions. Whenever we achieve this one, you will give a reward function so that the actor will activate. So this is the UAV environment we created, hybrid power sensing system. Then solar module, we are also having a solar module. So overall radiation and the actual power, because then flight dynamics and load estimation. So this DQN algorithm continuously how much power required for the next stage. So they will estimate the load and depending upon the UAE flight dynamics. So as per the DQL algorithm, we achieved the, so these are the energy consumption and source contribution for the flight forces. The climb, you can see fuel cell, battery, supercapacitor and load. Suppose during the climb stage, so the total load energy is shared by battery and fuel cell. During the cruise mode, because fuel cell will act as very slowly, so fuel cell slowly, that's why it is cruise control, we require a constant power, that it is. Then endurance also a constant cruise. Then maximum velocity you need more thrust, high power required. So this contribution, we have a fuel cell, battery and a supercapacitor energy. During the takeoff also, this is the power energy consumption over the different flight paths. So now you will see the complementary benefits of fuel cell and battery power over the long duration. We run this for the long duration, how much complementation. You can see the curves, they are complement to each other, right? Then you can see the simulated battery SOC over here. So you can see SOC low threshold is 20%. You can see almost 90%. So this is the 90%. So it is operated at almost near the band region, high band region. So low SOC is rolled threshold, high SOC is 0.9. And you can see the DC bus voltage over the flight time, it is operating at the same 28 volts. Then you can see the four combination fuel cell power, battery source, all each are complementing to each other. Two are, as we see in the previous bar chart, the complementary analysis, they are working for the long duration. We implemented for long duration time. Previously we analyzed for only 300, now it is for 1000 seconds. So fuel cell, how they are complementing to each other. Then you see the battery SOC performance is remains same. Then converter losses, as we told that we have the losses also, power losses, so which will borne by fuel cell and battery, so which have the complementation. Then SOC of the battery with no losses, SOC battery with losses, because threshold between. Then BLDC motor current over time. During the thrust, we have more current, cruising mode, descending. So the current also following the same as the power consumption. So then battery SOC comparison for the SOC comparison for this DQN agent means this is a RL strategy versus rule-based strategy. First, we have used a rule-based strategy. So DQN, we have, there is a decrease in the SOC. So these are the limits. Previously in all approaches, we have constant value. There is a decrease in the battery. Then fuel cell and battery, DTN versus fuel cell power versus battery. In both the cases, how they are complementing. Means in each strategy, how they are behaving, complementing the strategy. So power allocation over flight paths. So this is the different flight paths, the fuel cell power, supercapacitor power, and total power demand met by the source. And this is the power allocation over critical battery. This is flight path. So you can see different storage devices will support during the different flight paths to get the longer endurance. You can see more than 1,000 seconds also you are seeing, means we are achieved with the long endurance strategy. So now we applied with the rule-based strategy, machine learning approach, and MPC based, that is then deep learning approach also we approach. So we have four total performance evaluators: total hydrogen consumed, hydrogen utilization, battery SOC, and battery energy. We have taken only with respect to the hydrogen fuel cell and battery only. You can we can run we can extend this to the supercapacitor as well as the solar system also. You can implement with the different performance evaluators. So you can see there is a hydrogen consume. So the very less in the deep learning approach. Hydrogen utilization almost the same for every then battery is SOC is increased in the deep learning approach. Battery utilization, energy utilization also almost battery utilization reduced because of complementing nature of the components, which is perfectly work in the deep learning approach. So this deep learning approach of energy management system will provide for longer endurance, longer flight time can be achieved with the hybrid energy storage sources. So now what are the challenges come across during this policy is this is actually a simulation work, not the practical work. So there, if you go for practical, you will achieve much more difficulties. So first challenge is integration challenges of hybrid sources. Then lightweight computation method for onboard device, onboard EMS. Now we have simulation all there in the system. How to integrate in the onboard? It is also, as I mentioned, the weight, design weight, it is almost 20 kg. So we need to go for the lightweight competition methods for onboard EMSs. Then limitation of multi-agent. If we achieved good accuracy over the deep reinforcement learning. So limitations of multi-agent, we run with the only one agent only. So if you go for the multi-agent system, which is more appropriate, but it is a difficulty with the MATLAB, or maybe now we are getting the different advanced tools so that it can possible. Then there is a research gap with the energy aware path planning, because now we have a limited path planning. If you take the real time scenario, it is different. So we have to go for the more research on energy aware path planning. Then the future trends may be what we can implement further in this area is multi-phase EMS with fuzzy logic and low pass filtering. So what advantage we will get if you implement with this one is combines the low pass filtering, handles the rapid load changes with a fuzzy logic, optimizes the power distribution on a high computational efficiency. Then co-optimization of motion planning and EMS, because now motion planning is all the sensors and movement. Motion planning mainly it with respect to the wind speed or any adverse environmental effects will also. So bidirectional coupling of motional planning and EMS improves the energy efficiency by reducing the hydrogen consumption. Next, much more renewable integration as well as wireless charging. Combining fuel cell, batteries, and solar cell can improve the endurance and enhance the sustainability. If you use more of fuel cells and solar cells, it will enhances the sustainability. Then you can implement with the advanced optimization control techniques. So it improves the more flight endurance, fuel cell durability, reduce the hydrogen. So these are the different future innovations you may incorporate in this hybrid UAVs to get much more endurances and much more durability and efficiency. So thank you very much for your patient listening. Thank you very much for giving me opportunity to share my knowledge. A small amount of knowledge I share. Thank you very much for this. opportunity. That's all from my side. If you have any queries, you can.